Okay, it is 9 a.m. Pacific time, so let's convene the panel. I want to make sure that we have all the panelists here and they are able to participate. So if you are a panel member, like, is Chris here? Chris Howk. There he is.
Yep.
Turn on your camera. I see you. Gurtina, I see you. Edmund, I see you. And then I saw Freeke earlier. And there she is. She's out. In fact, she is raising her hand. She is at the head of at my Zoom grid. Actually, how about we let Freeke has her hand raised, so we will let her ask a question first.
Joe was first though, but thank you. I'm very glad that you got to the magnetic fields part, but I have a question about this because I'm not very good at observational coordinates. So what I saw was like from the H1 that it was all oriented in the same direction, and my question to Mary is like, which direction is this over what kind of scale? Like physical scale was that, and what does it tell us about the flow of gas in the CGM there?
Yeah, I wouldn't say that I would say it was all in the same direction. We did in the lowest velocity part of that IVC, it was going in the filaments were going in the same direction, but then for the highest velocity, we actually saw them start to go in another direction. But I would say this is early days on saying that the filaments are definitely tracing the magnetic field. We've known since we first started taking observations of HVCs, the Magellanic Stream is a prime example, that H1 clouds tend to have this kind of overall large-scale filamentary structure. So, but I think it's an interesting possibility, given what we found for the H1 filaments in our own galaxy, that we could have a continuation of mapping this. And then in terms of, this is all lower halo, same thing with the rotation measure results, this is lower halo, and in terms of the flow, I can't say. We did look for signatures of flows along the filaments to see flows along field lines. We did not see that across.
I assume the magnetic fields would be oriented in the same direction as the flow of gas.
Yeah, and so we've looked at that. We're not finding. Actually, we haven't looked at large-scale bulk flow too much. We so far what we've done is we're looking for flows along the individual filaments, which you might expect, right? And we're not seeing that. And we have 0.18 kilometers per second resolution, right? 180 meters per second resolution. So it's pretty good. And we're not seeing clear flows along the filaments.
Thanks.
Okay, Joe, I'm going to have you ask your question. And feel free to ask to the panel as well.
Thanks. Yeah. So I brought this up in the Slack just now, but on the point of the Milky Way and M31 dwarfs being, perhaps more gas poor and more likely to be quenched than those around other galaxies, in your representation of the Milky Way and M31 systems, Mary, you had it looked like the dwarf galaxies that we know about are actually pretty strongly clustered in this sort of inner regions of the respective halos. And so I'm just curious if maybe, and anyone on the panel can comment here, but if maybe the fact that those dwarf galaxies have gone further in their infall and perhaps have undergone the ram pressure stripping more so than satellites around other systems, and maybe it's just an evolutionary dynamical state thing.
So in general, we don't consider the local group a highly evolved dynamical state. It's not settled. So, but your question is just that the satellites originated earlier somehow in our system, that they've had more time to undergo the stripping process. So this goes back to the comparison with simulations. And so there's work, for instance, by Christine Simpson, and there's some others as well, it's not coming to mind, but where they actually look at the simulations and what you expect. And indeed, they do see that stripping is common, and that that you would reproduce that type of result. The other thing they find is that there are lots of what are called splashback galaxies. So the ones that are beyond the virial radius without gas, they can easily be explained as ones that have come in and been stripped and they're now towards the edges there. So that could even explain those ones that are stripped that are towards the outskirts. So I don't think I'm quite answering your question. Actually, Gurtina, do you want to comment on this?
Yeah, sure. I don't think there's any evidence that the orbital properties of the satellites around the Milky Way or M31 are particularly odd as a population. So, it's not clear why these two systems would have the dynamics such that everything stays in the very center, and then all the other ones that we're seeing with the Saga survey, for example, have completely different dynamics. That would cause the difference. That would explain this. Yeah.
Can I follow up on this a second? So, how much the fact that in the Milky Way you're counting also extremely small galaxies like the ultra faint dwarfs that you will never see probably in these surveys, how much a difference does it make?
Yeah, so with Saga, they actually did an accounting of the ones in the Milky Way that are detectable by their survey, right? And so that's the same thing we're doing with looking at other systems now with Jingmiao. We're looking at what we can detect in these other systems, and once you take that population, the ones you can detect, how do things compare? And so even just taking the ones we can detect, we're finding differences, that the local group dwarf galaxies are more quenched.
Can I add something? Right.
Please.
But there's another issue, and that's that you've shown nicely that if you go outside of the virial radius and you're looking out to a few virial radii, you see a lot of gas-rich galaxies. And in the Saga survey, they will not be able to discriminate those from galaxies that are inside of virial radius. They're in the inflow pattern. They have exactly the same line of sight kinematics. So doesn't that just explain the situation? In the Milky Way, we're specifically counting things out to the virial radius, but we should probably be counting everything that has the same line of sight velocity.
I don't recall how they're doing that exactly for getting their distances. Do you?
I don't think they can.
Yeah.
They just
I
get a
think you're
velocity.
probably right. I should look at that. That makes me think I need to look at that more closely, because we're doing the same thing in terms of looking in H1 where we have to use the velocities for the satellites, right? And so then what we're going to do is project the whole local group and see how many you would expect to detect. And indeed, once you project the entire local group, you get in those gaseous ones. So your point is exactly what we're considering now, and I hadn't looked at what Saga does with that regard.
Okay, I'm going to take moderator's privilege and ask a question I have, and then we're going to get to Joel and Smita. But I think it's a question that they might like as well, and that is the Milky Way's hot halo has constraints from Xray emission, Xray absorption, Magellan extreme pressure, equilibrium, and now dwarf satellite stripping statistics from Mary's recent paper. Are we able to build a consistent model of the Milky Way hot halo from these heterogeneous observational probes? And this is for the panel as well.
I think Edmund, do you want to take a first crack at that?
Yeah, I mean, I think that given the constraints that we have, it is possible to create a self-consistent picture of the Milky Way hot halo. And one of the main problems right now is that those constraints do not lead you to a unique solution for what that hot halo looks like. And I think to a large extent, we're very much still at the point where whatever model you assume that when you put in is going to determine what you get out. If you are using something that is primarily working with a lot of emission line data, you're going to be much more sensitive to what's going on in the disk and the disk halo interface. If you are using absorption, you're going to be more sensitive to what's going on at large distances. If you assume that the Milky Way hot halo and the hot ISM and the disk are more or less a contiguous system, and you combine the information from absorption to X-ray binaries in the disk with the sight lines to AGN behind the halo, then that leads you to yet another mass model. So I think that we are able to use those constraints, and I hope that we will iterate and reach something, we'll converge to a single answer eventually, but I don't think we're there yet. But I would like to highlight that the HaloSat papers are starting to come out. This is the first astrophysics CubeSat, and I don't know if Phil is on the line, but I think Jesse is on. And so Phil published a paper on an analysis of the southern halo, and one of the main results from that was that the emission is fairly clumpy. Jesse is now going to publish or he's working on a paper analyzing the north and south halo data, and so I think that that's going to be a major improvement over what we got from ROSAT, and I think that will help quite a bit in terms of the emission line side. I don't know if it will completely solve the uniqueness problem.
I don't know if anyone else wants to add to that. I don't think I have anything to add.
Okay.
You want to let Joel say something, and then he
yeah, I think so. I think that's a great question. Yeah, let's Joel. You had your hand raised for a while, so go ahead.
Okay, so let me make a few points. First, which I published on in 2018, is that there is certainly a difference between the Milky Way and COS halos, which is 2.5 gigayears earlier in time. But the Milky Way isn't, lowish columns that one sees in the Milky Way isn't all that different than the low-Z galaxies that the COS team, Stocky and company, published. So it may be that there's just been more evolution in that regard than we thought in the last 2.5 gigayears. Moving on to something else, we do have a number of constraints on the hot X-ray emitting halo of the Milky Way. It really only goes out to about 50 kiloparsecs, and then we're extrapolating. But one of the new things, we seem to see halos around other galaxies from SC work. I'll put something on Slack soon. But one of the things that's come out that's rather new is from Sunyaev Zeldovich observations of our local group. You see a hot bridge in the direction of, between the Milky Way and M31. This is also the direction where a lot of dwarfs, such as the LMC and SMC, have come through. The density is higher there than in, say, other directions. And so you might expect more stripping. So when you consider stripping models, you should.
Well, we looked into this. We don't have the data to say what the orbits exactly are doing. We tried to see if they did preferentially pass through that inner region, and you can't say that.
Okay, well, I thought you could for.
I mean, it's likely. I mean, Gurtina could say a lot about this. Actually, we should probably.
Yeah, so Monica Valori, who's my expert on this, is the one who told me that the LMC and SMC came through in that direction based on proper motion.
Oh, sorry, I thought you were making a general.
No. No. So, in any case, that's. All I want to say, in other galaxies, we find that the hot halo out to about 250 kiloparsecs is comparable to the stellar mass. Okay, that's about it.
Okay, so no question there. Okay, Ben, should I keep letting you moderate, or I'm wondering what you suggest is the best way to do this? Like, there's people raising their hands. There's a lot of questions in the chat, in the Slack. So I guess. What do you want to just encourage people who ask questions in the Slack to raise their hand? Is that what you want to do? And
yeah, I think
otherwise, I'll just say, and otherwise, if I can see that Jess and Young have already helped answer questions, so that's great. And then I'll go in after this and make sure I try to answer any odds and ends as well in the panel.
I think we want to hear from Smita. She's had her hand up patiently for a while. And then I'm going to try to get some more of the panel members involved, because we haven't heard from Chris yet, and I definitely want to hear on the cool side of
That
stuff
sounds good.
comparing to Andromeda. So Smita, go ahead.
Yeah, so I just wanted to say that I do agree with Edmund and things that he has said about the evidence that we have from emission in X-rays, and HaloSat and new E-Rosetta results are really making a difference. But it is very important to keep in mind that the column density, as we infer from these regions which are emitting, which are very dense regions and clumpy regions, are too low to explain absorption data. So there is no getting around the fact, and Phil Corrett would agree with that too. In fact, he did at the AAS special session we had in June, is that there is no getting around the fact that the hot medium in the Milky Way CGM that we see in absorption is very diffuse and extended. And I wanted to comment at your talk, Mary, by the way, great talk, great lot of good work, is that your work also suggests that there is actually a lot of hot gas, as you showed by the gas that is required to strip the galaxy that you are talking about. So there is actually a lot of mass in the Milky Way CGM, as we saw, and that even the average density of the order of 10 to the minus 4 per centimeter cube is very reasonable. It's very similar to what you actually get from absorption line studies also, and looking at comparison of absorption and emission. So while it is true that we do not have a unique solution yet, and I would be the first to admit that our understanding of even the hot Milky Way CGM is evolving as new data are coming, but we are very much coming to a consensus. And so, Mary, what I wanted to say when you after your talk is that when you say there isn't as much mass, I think there is the qualifier of cool and warm gas, and that there is actually more mass in other phase, which is the hot phase. So that was the thing I wanted to mention. Okay. And the other comment I wanted to make, because you mentioned halo gas, is that I basically wanted to talk about new work that we have been doing, and that here I do definitely want to talk about the work of Sanskriti Das, who is my student, is that she's making new grounds with very deep H1 data. And in extended galaxies, we are actually reaching the column density of 10 to the power 16 per centimeter squared. And so seeing diffuse low column density, very extended gas out to 100 kiloparsecs. So that's a fun new thing.
That sounds like something we should talk about later. 10 to the 16, you must be smoothing by like 100 kilometers per second or something. So that's very tricky, but we should definitely talk about that later. Yeah. Ben, why don't you go ahead to...
Yeah, Todd, I do want to get to Todd. He has a follow-up comment to the Losey hypothesis.
Thanks, man. So just a quick comment on this idea that the Milky Way is different because of time evolution. Well, the Milky Way is not the only galaxy that we've studied in the nearby universe. I'll just give you one example. Dave Bowen did a really nice study of NGC 1097, which is, 10 or 15 megaparsecs away. And he looked at not one, but 4 quasar sightlines behind NGC 1097, and now he has 3 more. And you can look at that paper, and the H1 in the halo of NGC 1097 looks very much like the COS halos at comparable distances, say 100 kiloparsecs. So I don't think that it's a matter of evolution between when the COS halos galaxies were observed and the nearby universe. So, there's more to life.
Ben, Todd, sorry. Does it have a satellite system through it or something? Because it's very rare to detect those. The point is, and Chris made that point in one of the questions in Slack I saw, the high column densities at large radii. I mean, you definitely get Lyman alpha absorption in local galaxies, but those types of high column densities, the only time you've seen that in H1 emission surveys is when there's a satellite system coming in.
Right, but of course, COS halos, which is what we were comparing to, is not looking at those high column densities so often. Much of the COS halos columns are not detectable.
Well, except the top, but the mass of those COS halo sightlines is dominated by the very high column density sightlines. And so when we did the comparison with M31, what stood out in particular was a lack of very high column density systems like you see in cos halos. And so, I mean, it is true that on the whole, the number of sightlines that probe relatively high column densities might be smaller, but they really dominate the statistics in that sense in some ways. So that was the point of the comparison.
I don't want to be contrary, and maybe this is an interesting discussion that we can have, but I'm not sure that a high H1 column density reflects a high mass, because of course there's a big honk in ionization correction. So if you see something with an H1 column density of 10 to the 14, it's very hard to get the mass. And I mean, in all these things, probably most of the mass is in the ionized gas. So I'm not sure that
Oh, absolutely. So,
yeah, that may be.
Except that the silicon-2 and things like that tend to scale with the H1, of course, right? So that does play a difference. And you're right, there's an ionization correction, unless you can do the trick, which cos halos have done, and we've done it in 31, of adding together silicon-2, 3, and 4 to get sort of the combined warm gas. So I mean, my point would be on that, Todd, that, you know, M31, for example, is down by factors of a couple in those intermediate and low ion column densities from cos halos. So it is different in that regard. But the 06 doesn't change that much. So I mean, I'm not 100% disagreeing with you, except to say that yes, there are lots of ways to tabulate that. So
I guess the main point that I wanted to make is that we can look at other galaxies besides the Milky Way in the nearby universe, and in that way we can see if there's something peculiar about the Milky Way, which would be interesting in its own right. Thanks.
Yeah, I think that's,
yeah,
I think that's something, when I was thinking about this, that I felt like maybe hadn't been done at the level it could be done, in terms of taking all the local galaxies, doing exactly the same census of mass, etc., and seeing what you get, because there's enough archival data now to do that.
Gurtina has a comment or a question.
Yeah, I just wanted to add in that when we're talking about comparing it, you know, at the right time, so if some system for cos halos are at an earlier stage, it's not just in terms of literal time, but it's also in terms of evolutionary stage. So one thing to bear in mind is that, you know, the LMC will likely merge with the Milky Way in about 2 billion years. And after that, it's expected that a lot of the properties about the Milky Way may become much more typical of the comparison to other comparably massed galaxies. So its stellar halo, for example, is fairly low in metallicity, and Marius Kauton had a really nice paper which shows that, you know, if you add in the LMC stars, suddenly the stellar halo of the Milky Way becomes much more normal. So there are a lot of properties that, you know, give it 2 billion years, and suddenly the Milky Way will be a different system, and you'll be comparing to a different point. So you have to sort of compare apples to apples. Most galaxies have an LMC type analog that they've eaten at some point in the past if they're Milky Way scale. It's one of the major building blocks. And so you do need to keep that in mind. Whereas the Milky Way hasn't actually had a merger with an object as massive as the LMC in the past 10 billion years, right? So it's at a different stage.
That's a great point. I just put in a question in the Slack. Jonathan Stern has been waiting patiently, and I'm excited about his question.
Yeah, thanks. Yeah, I have a question about the association between the 06 and the H1, like Mary mentioned in her talk. So it's right when we look at close halos, right? We see that the relation between the 06 column and the impact parameter is very different from when we look at the H1 or in the low ions. And kind of the 06 has much more flat relation with impact parameter, which kind of suggests it comes from much larger scales than kind of the low ions and the large H1 columns. Okay? And then Barry, you kind of said that there's this evidence that they seem to be in the same place, right? That there's some strong association. So I'm kind of trying to understand how to reconcile these two things. If you have any comment on that.
Yeah, I think I'll let Chris say more on this for sure, but when we look at the Milky Way, I'm just bringing up that plot, but I don't think I need to share it again. It's largely at very similar velocities, and this is a point Ken Sunbach made in his paper, that you see it overall follows the structure of the H1 complexes, except for there were a few interesting sightlines, maybe local group medium, which Richter has also followed up on these sightlines that don't follow the overall structure of the H1 and other ionized gas components. So you do, which does indicate at least for the Milky Way, what we're detecting is stuff that is associated with the other phases. Chris, you might have even been on those papers. You want to say more?
Well, except that I lost Jonathan's question about halfway through. Except, so I think even some of the 06 that was identified as sort of local group in that Simbach paper have turned out to be associated with M31, we now believe. So, I mean, they're certainly there. But yes, in general, you know, in the Milky Way and the LMC, in the sightlines between the Milky Way and the LMC, if you look at the extrema of the 06 absorption, it's always within the extrema of the low ion absorption. And oftentimes, when you look at sort of individual locations, especially for the high velocity clouds, they tend to be pretty similar, at least in velocity along the line of sight. But that's, I'm guessing kind of what the question was, so just based on Mary's answer.
Yeah. So, I mean, at least for Cos-Halos, it seems that the 06 is more distant than at least the low ions in the large. So I'm just thinking, is this correspondence in velocity, does that necessarily tell us that they're co-spatial, or maybe it's just some large-scale velocity structure in the halo? Or is it a difference between the Milky Way and Cos-Halos? I mean, that's the only two possibilities I can see.
And are you thinking, just so for clarification, are you thinking the 06 specifically associated with, for example, the high velocity clouds and Magellan Extreme and such, or just more generally everything that we see?
So you were saying, but the velocities of 06 seem to be correlated with the velocities of the H1, right? That's the observation.
Yeah, for other systems, Jess, do you want to say more on this in terms of the location of the 06?
Yeah, so I was going to chime in. I mean, kinematically, that's absolutely what we see around Cos-Halos. I think there's no difference. I mean, if you look at the kinematics of 06 and the low ions, even 80%, right? I quantified this in 2016. 80% of the low ions in 06 are kinematically aligned in terms of the velocity centroids of the different components. 06 looks different, though. There is a lot of 06. It's broader. And I think that the difference, Jonathan, I think part of it is ionization state. So when you're just looking at bulk column density trends with impact parameter, I think that there might be some kind of ionization transition, like in the halo, some density transition too, that happens around like 75 kiloparsecs or so. 06 doesn't drop off nearly as quickly as the low ions, but it's hard to, I don't think you can make the jump then that 06 is coming from larger, actual distances from the galaxy.
But if it's not dropping as fast with impact parameter, doesn't that tell us that it's located farther away? Or at least some of it is located farther away?
Well, maybe you're not seeing the low ions because they've transitioned to a higher ionization state, right?
Yeah,
That's right.
In other words, silicon 2 or 3 that you would pick up at 50 kiloparsecs might be just so weak relative to the 06. It doesn't necessarily mean they're not coming together. It just means the radial drop off is different. So it doesn't exclude that, I would say. But Todd, has shown, and showed the other day, last week, 2 weeks ago, lots of examples of that that's sort of consistent with what Jess sees, where the 06 and low ions are very well correlated. Now,
in velocity,
perhaps
I entirely agree with the correlation with velocity. I guess just the fact that the 06 doesn't drop with impact parameter to me suggests that it's far away, regardless of where the low ions are. Just the fact that it's a flat relation, if you just deproject that, without any assumptions, too much assumptions, if you get that the 06, I think, is more distant, or at least most of it. So maybe I'm missing something, but that's kind of my impression from Cos-Halos.
It's not just the velocity extrema, it's also the component structure. And Gwen has showed this, and I've showed this. The components go up and down in H1, and the components go up and down in oxygen 6, and the centroids track along. And that statement that Chris made can be applied in a lot of contexts. We see that in the Milky Way disk. The extreme of the low ion absorption in the Milky Way disk is the same as the extreme of the oxygen 6. I think it's very strong evidence that oxygen 6 has some kind of profound connection to the lower ionization gas. I don't think it's volume filling. I think it's some kind of interface phenomena or the other things that folks like Drummond and Max and Evan and all kinds of people have been talking about. The volume filling phase, I'm guessing is what we see in 07 and 08 and maybe X-ray emission. I believe there's a hotter phase that we just don't really have access to when we look at ultraviolet absorption lines.
So Todd, I'm definitely not disagreeing about the correlation of velocity. So I think the evidence is there, both like you said, like you just said, both in cause halos and in the Milky Way data. There's a strong correlation in velocity between the high ion, the O6 and the low ions. What kind of puzzles me is the very different relation between column and impact parameter between the O6 and the low ions. And that's hard for me to explain in kind of a co-spatial picture, right? If O6, in extreme sense where O6 would exist wherever there's low ions and vice versa, they would have the same relation, same trends with impact parameter, and they clearly don't.
Yeah, what I think is happening is that as you go farther out, the stuff becomes more ionized. Maybe the densities drop or the physical conditions change. And so then when that happens, the only things that are really sensitive enough to see the material are oxygen 6 and H1. And the other ions just become really hard to see. There could also be metallicity effects, but that's my guess. I mean, I agree with your point. It is an important piece of information. So,
okay, let's move this conversation along. I see Kirill patiently raising his hand, and we want to hear from new people. So please ask your question.
This is actually also about the same subject, but this is a specific case for the Milky Way where you can kind of test this out. So there is the this is actually sort of a classic Howk and Leonard reference. There is there's a big kind of HVC, or probably multiple HVCs at this point, seen towards the Large Magellanic Cloud. Right, there's 06. And this is seen towards, tens of stars, almost 100 stars in that direction. Now, there's 06 towards most of them, if I remember correctly from those papers. But the interesting thing is, as it's turned out, at least some of that HVC is most likely actually quite close. There's a very funky white dwarf that was found in that direction, which shouldn't be very far away. And I would have to dig into the papers to make sure, but I think the 06 properties of the two, of sort of the part that's probably in front of this star and the part that is plausibly farther away and actually close to the LMC, the 06 properties are pretty comparable. And so in that sense, right, that's got to tell you some of the 06 can't be very far away, and going very far away from the, or not very far, but going 40 kiloparsecs away out to the distance of the LMC or so, versus going maybe 10 kiloparsecs away. That's sort of the distance to this white dwarf. Doesn't make a big change if you're looking in the Milky Way for the 06. So at least in the Milky Way, it seems like the 06 is quite plausibly not very far away. But I guess, right, to really...
Then you also have it along the entire Magellanic system, where we think the tail goes out to 100 kiloparsecs, right? So that actually, Jonathan, that Milky Way data set may be useful for you to think about more, given we have what Kirill said, what Kirill described, as well as the Magellanic system, which probes what's going on with 06 in the outer halo.
Okay, I want to switch gears and address Greg Bryan's question, as is there a consensus to the origin of the high velocity clouds, and are these a significant contribution to the Milky Way mass and angular momentum?
The origin, no. So except for the Magellanic system, it's still the same, that there isn't consensus. The metallicities are range 0.1 to 0.4, depending on where you are in the sky. There's a lot to be done yet with metallicities. Actually, I think Bart Walker is working on some data related to that. And so no, we don't know. I mean, it could be gas that's recooling close to the disk, now that we know it's all closer to the disk, and it's maybe a mixture of all the different gas, some of the Magellanic stuff that's come down. ionize, and then it gets closer to disk and begins to recool out. We don't know the exact origin. Mass contribution is nil. I love Jess had this pie diagram where she used to make fun of that, like HVC 0%, right? So in terms of their mass contribution, it's negligible. That's talking about the H1, and when you bring in the ionized, again, because they're all close to the disk, it's still not much when you bring in the ionized, given that they're all here, and most of the mass would be, out here in the large volume.
Yeah, the ionized gas is 10 times the H1, but when you're multiplying 0 by 10, you don't get much, right?
And that's even true if, sorry, just to quickly follow on, that's even true if you account for the fact that it's close to the disk and so presumably accreting rapidly, so may not exist in that state for very long. So it's like a flux question.
Oh, you mean in terms of the infall rate they provide?
Yes, exactly.
Oh, okay. So it depends on how exactly you do the inflow rate, but you get about 0.2 to 1 solar masses per year. Given their low z height and relative velocities, you have to make some assumptions about their 3D motions with that. And then the Magellanic system is a whole separate one. As Gurtina mentioned, that's going to be, Milky Way is going to love that. It's having a feast once that comes in, but that does not include thinking about the Magellanic system. So in that sense, yeah, you could argue they are significant in terms of they're providing a decent amount of ongoing fuel if they have to be continually reproduced, though. That's key. You need to continually be cooling out that material because we don't see it otherwise besides the Magellanic system.
Could there be inflow coming from the disk plane that we can't see because of our solar perspective?
Yeah, that's an interesting question. Not at high velocity, but you might not expect it to be at high velocity once it's. So people have tried to look at this, and there are constraints, but and there are a couple papers. I'm thinking of one Erin de Block put out with a student for NGC 2915, where they are seeing some flows along the radial axis along the major axis of galaxies. For the Milky Way, I haven't heard anyone try to make that claim yet. Karel, do you have any insight into that?
Flows in the plane of the Milky Way?
Yeah, going inward.
Inward?
The gas?
I think Josh wrote a paper where he tried to look at that, but I think the signal would be very weak. I know, right, there's been people have looked for this in other galaxies. So I think Tony Wong has a nice paper looking at H1, I think probably H1 dynamics in a few local galaxies, right, like trying to decompose the velocity field into a variety of kinds of flow. But I think there the conclusion was that, well, first of all, it would be pretty degenerate with other kinds of motion, other kinds of non-axis symmetric motion, and the constraints that come out aren't like super great.
Exactly, yeah.
My recollection is this problem, and people asking that goes back decades, and they always seem to have sort of limits where they say you can't quite do it or we don't quite see it. But maybe that's the wrong impression too. So,
I guess there's
they give limits of a few solar masses per year flowing radially in the disk, right?
Yeah.
Can I add a couple of things briefly? I'm going to discuss these things in my talk, but just that we are mentioning this. So there may be inflow within the galactic phantom cycle, so that we see in terms of intermediate velocity clouds. And I mean, I tend to see these days this high velocity clouds like an extreme version of intermediate velocity clouds. I don't think that somehow there is a divide between the two that decided by Bart Bakker 20 years ago, or what was it, 30 years ago. So I mean, there may be, and there should be much more inflow there. The other thing that I wanted to say is that in external galaxies, especially, several people have tried to measure the radial velocities in the disk to see if there is this radial inflow, and usually the values are very low, or you don't see it. So it's there isn't an evidence of really, I mean, galactic disks behaving like efficient accretion disks. put it like this. So we are talking about 1 kilometers per second to 1 or 2, something like this, if it's there.
Okay, I'm gonna switch gears a little bit because John Chisholm has a great question, and I'm really interested in this. Could there be any recent impact from AGN activity in the Milky Way setting the CGM ionization state in the halo? And we think about the Fermi bubbles and the Rosetta bubbles and our Sagittarius star central black hole. So I pose that to the panel.
Yeah, I realize that's something I did not touch on, and I haven't followed that literature as well, so I can let other people answer that. My understanding was it doesn't go out that far, but why does I don't know if Chris or if we want to bring in Wrongman or something to answer that further. Chris, do you want to start? Or maybe Edmund?
Oh, yeah, Edmund might have a better idea, or even Freeke in terms of her simulation work. But so it might depend a little bit on what we're asking. So Jocelyn Hawthorne has been talking about the idea that there are ionization inconsistencies along the Magellan extreme that could in part be caused by illumination from an AGN. Now that would be radiative feedback. So that seemed not unreasonable when I read it, and they have some good evidence for it. It's maybe not a solved problem. But I'll let others weigh in on perhaps the mechanical aspects of that, because they would know definitely better than I would.
But so wouldn't it? The radiative feedback is what I'm kind of implying by all this, because
so you're thinking essentially like in the precipitation case, if you get a case where you turn on that AGN and illuminate the CGM so that it's in a state where it's not likely to cool and condense, unless we can't see it perhaps in the UV absorption that we see, for example. And that's potentially plausible. I don't know. I mean, the Magellan extreme potentially provides, just because of the time delay for recombination and also for when you shut off the AGN for that information to propagate out there, it potentially provides something of a handle on that. Now, as to whether we could say, there's other evidence for that, I truly don't know, aside from, I mean, that could be an argument that you make for the differences, I suppose.
Yeah, I can just say for the stream, yeah, we've puzzled about this bright region of the stream that's right above the pole, but that's also a region that has this interesting cross complex of clouds and stuff like that. I mean, when I was a graduate student, I pointed out to Josh, I said, look, it's right above the galactic center. Maybe there's some, and he dismissed it at that time. Then the Fermi bubbles came out, and now he thinks that, it's outflow from there. I also was wondering about the timing of this. I don't know, Gurtina, if you're thinking about the time scales of the system and it being exactly overhead, does that actually work out correctly that the bright patch would be there?
So the closest approach of the LMC to the Milky Way was 50 million years ago. So in order for the stream to be in that location, you have less than 50 million years. So as long as the time scale is within that, there could be some overlap.
Time scale is a couple of million years, so it works out very nicely. But it's a very localized effect in the sense that it's very directional, where the sort of the jet, if there was one from a Fermi bubble, will point towards. So I don't know if it'll affect the whole of the Milky Way.
I'm going to say something about the radiative feedback because, Joss would be talking a lot if he was here and not asleep right now. But his 2016 paper with Phil Maloney, I think, was explaining the non-equilibrium effects of H alpha in the stream being enhanced by a Seifert burst of like several mega years ago. And then his more recent 2019 paper is, I think, carbon-4 and silicon-4. And, I've worked on the non-equilibrium effects of, flash ionizing something and the AGN turning off. And, you could have a Seifert burst and the timescales would be a few mega years for like things like carbon-4, silicon-4, oxygen-6, for those to last residually in the halo at elevated levels.
So, just Ben, since you're finding about that, which is great. I suppose one question though becomes: is it possible? I mean, with the narrow opening angle that might be suggested by what we see in the stream, I mean, can you affect the whole of the halo like that in order to suppress something like O6 or the low ions or something?
I mean, like how much of the what's the opening angle of the AGN radiation escaping? I mean, that goes to the torus models around the AGN. I think you can definitely, pretty much come up with any sort of model where it's like, 2 pi steradians or.
Well, except that here you have a little bit of geometric information from, if that claim is the correct one, you have a little bit of information from the properties of the stream and the angle over which that's affected, right?
And that was in Joss's 2019 paper.
So I think that one point on this is that if the Fermi bubbles were created by outbursts from Sagittarius star, which is my personal belief is that that's the best interpretation, that limits the age to within the past, I don't know, like 8 million years based on most of the models. And that's fine, but we don't know if this was a one-off. We don't know how often this happens. And in order for the Milky Way's whole halo to sort of be perturbed to the point by the ionization structure to be continuously perturbed by AGN, then we would sort of need Fermi bubbles to be happening on a regular basis if these bubbles always accompany the radiative feedback as well. That is, if the AGN turns on, say, every 10 million years and dumps out a lot of ionizing radiation, then maybe you can explain some of the halo ionization ratios that way. But in that case, we would also expect to see sort of a cascade of Fermi bubbles, that those things, as long as you always get mechanical feedback along with the radiative feedback. So if everything is like a Fermi bubble type outburst, which it may not be. And there's not really any evidence for that. These bubbles are going to continue to expand. We kind of understand their expansion rate in a couple wavelengths. And if you were to produce these things every 10 million years, every 20 million years, we ought to see more stuff piling up than we do in like the eRosita maps, for example. So it seems to me that there has to be a fairly long time period between outbursts. So if there's an ionization balance change due to the outburst that created the Fermi bubbles, that is probably not how the Milky Way, quote unquote, normally is.
Can I have a quick comment?
Sure.
So I think there is some evidence for things being different around the shells, right? Because, we definitely see a lot of emission around the shells of Fermi bubble and eRosita bubble, but I think we are also seeing different temperatures. Like everywhere else that we see X-ray gas, we do see few million degree gas, but around the shells, we have very clear evidence, and in gas that we see in emission, let me qualify that again, it's in emission, we also see hotter temperatures closer to 10 million kelvins. And so even therefore in these hot regime, we see multi-phase gas, and that gas is very much around these bubbles, which is not necessarily restricted to those regions, but we definitely have very clear evidence of higher temperature gas around those shells, and there is higher emissivity in those gas also. So there is definitely impact. It has impacted the ionization balance. We are seeing ions we don't see otherwise, like neon tan, right? So that is, has the feedback from AGN or starburst activity. I think it should be feedback, but anyway, that's debated. Is that affecting the ionization balance? It definitely is, because we don't see those ions everywhere else.
Okay, great. We have about 12 minutes left, and Daniel has had his hand raised for a while, so we're going to go to him next, and then Tim Heckman has his hand, and we're going to try to do those 2 questions. So Daniel, go ahead.
Okay, thank you. I have actually a couple of questions. Let me go first one. I mean, Todd and I have been trying to do some UV absorption line studies and to understand the gas in the local group. And I'm sure a lot more people are working on, have been working on these issues. So you have actually different distances, for example, to the M33, M31, so to some of the other galaxies. And so you have absorption lines. So whether that, to differential kind of absorption line studies at large distances will be able to tell you about the actual local group gas. And also what actually get an update on there's any kind of solid evidence points to not only the gas around individual galaxies, but also actually much larger scales centered probably around the center of the local group.
So your question is, what evidence is there from absorption line results?
Yeah. If there are any. Maybe there are quite a number of studies towards M33, towards M31, towards different other galaxies. So now actually more or less points towards the cross the center of the local group.
Yeah, specifically those, I mentioned the one's null result, and then Joel mentioned a recent result that I haven't looked at that paper yet, indicating there is something there. Otherwise, in terms of the UV, there's certain absorption lines that don't seem to fit with the rest of what we see for halo gas. And so people have pushed on those as potentially representing a local group medium. But along that axis particularly, there hasn't been strong evidence. The only other thing is the H1 clouds that have been found. In general, though, those are thought to be interactive debris probably, like with M33 in the past. But that was, for some time, that was also noted as something unique. But it's not, we don't have solid evidence between us and M31. Part of the problem is making that claim is difficult because of the velocity confusion when you're in the local group. To make that claim, you have to do some very heavy modeling, and people have to trust your model. And so it's just very difficult to make a claim that everyone jumps on the bandwagon and says that's it.
But you did mention some simulations, recent simulations. Do you expect, from theoretical point of view, do you expect large scale diffuse, say, halo, local group gas?
Yeah, you do. That's in the simulations. Ben, you want to comment? You're doing group simulation. Yeah. No, you do.
I'm too afraid.
In Hodder.
Not that type of group.
I think it'd be really difficult from the absorption line perspective because of the influence of the gas that might potentially be around those galaxies themselves. It's hard to disentangle that. Fast radio bursts might be, and the dispersion measures you get towards them might be the way to do this ultimately when we get enough of them. The local group barycenter is not exactly in the direction of M31, so maybe you can look for offsets and to build up a columnity that way. So yeah, but I'm with you. It's a hard question. One would be great to see the answer to.
Tim has had his hand up for a while, so let's hear from him.
Yeah, so I'm not really convinced that the E-Rosita bubbles are driven by an AGN. If you look at the energetics, it requires about 100,000 supernovae if it were driven by a star formation. So that's 10 to the 7 solar masses in stars formed over the dynamical age is about 20 million years. So that says if you have a half a solar mass per year forming in the central few kiloparsecs of the Milky Way, that you have enough energetics to drive this thing. And if you look at the E-Rosita bubble, I don't really see any evidence that it has a source that's very compact. It's quite broad at the base where it intersects the disk. So it could be driven by this 3 kiloparsec ring of star formation. So if there's, what am I getting wrong here?
Can I jump in?
Yeah, Kartik, go ahead.
Hi. So if you wait, I'm going to actually discuss this tomorrow, broadly. And I think what you were saying about a star function driven model can be true. And I have written few papers on this, which exactly matches your numbers. But I think this is still debatable. So maybe we can discuss this after tomorrow's tutorial in more details.
Sounds great.
From other people. Yeah, thank you.
I think this was Joss's model too in the early 2000s. Or
yes. Yeah, I think, yeah.
I mean, it is pretty centered, it seems like, on the, the very center of the galaxy, where Sagittarius star is, as opposed to like 3 kiloparsecs out. But I don't know how that.
That's not necessary. I mean, you can have 100 parsec star function region or 100 parsec, and that would still work.
So just to chime in on this, I mean, I don't have an answer, but there is now evidence for an Xray chimney from the Sagittarius star region pretty locally that seems to connect up to the Fermi bubbles. Whether or not that's just something that happened once they were already formed, or whether or not it's the driver, I don't know. But there's a lot of XMM time just awarded to study this further. So I think that we're going to get more insight onto the extent to which there is like an X-ray jet as has been claimed. And we might get more insight into the origin of the Fermi bubbles.
Yeah, but I mean, certainly Sagittarius star is not doing anything very dramatic right now. If over the last 20 million years, Sagittarius star is as active as it is now, it could never have driven the Fermi bubbles. It had to have been some explosive sort of event that's not happening right now, right?
Exactly, but if you look at the reflection spectrum from the like the fluorescent iron K alpha and the molecular clouds around Sagittarius star, with it, I mean, that does not go back the 3 million years needed to produce the Fermi bubbles, but we do know that within the past 500 to 1,000 years, Sagittarius star has had near Eddington outbursts, short-lived ones. But you know, it's not inconceivable that it had that something happened and it had a big outburst, and now it's quiet.
All right. Well, I've obviously stirred up a hornet's nest here, but it'd be good if we can talk more about it tomorrow.
Wait, did I miss that? 500 to 1,000 years? It's been at Eddington?
No. Within the past 500 to 1,000 years. So if you look at the X-ray emission, the iron K alpha emission from molecular clouds near the galactic center, you can work out from their distance, from the kinematics what their distance is to Sagittarius star. And so you can say, okay, well, if these things are this bright now, and you assume an isotropic radiation field from Sagittarius star, and you know the distance, then you can work out, you know, how long ago it was yay bright. And if you do that, then you get I don't know if you get to Eddington all the way, but you get pretty close to Eddington.
Sorry, I thought that was -4 Eddington, 10 to -4 Eddington. You're talking about the estimates by this Japanese group, right? So I thought that was close to like 10 to -3 to 10 to -4 Eddington.
For the most part, yes. But I think that there are a couple, I mean, to some extent, I don't want to derail this too much, but to some extent it has to do with how you model the fluorescence. But for some yield models, like not all the outbursts get up to Eddington, but like a couple get pretty close. So I think that, you know, if you build up the light curve of what you think Sagittarius star was doing, it has some pronounced peaks in it, and then now it's at like 10 to the -9. So regardless of what has actually happened, I think that there is pretty good evidence that it can have dramatic flare-ups and then return to this extremely quiescent level, which is way below almost any other black hole that we know.
I may comment on this a little bit. I mean, a few things relevant. And the fluorescent radiation, you can kind of infer something like 10 to 39 ergs per second in terms of radiation. So that's very tiny in terms of Eddington ratio. And the current quietness of the Sagittarius star is mostly due to because the young stars around, which produce very hot winds, basically prevent the cool gas getting into the black hole. That's quite reasonably understood. And because the age of this cluster is about a few million years, so you can imagine when the cluster of star was forming, and you could trigger the Sagittarius star activity. I think that's a time scale wise actually about right. And so in terms of the chimneys, X-ray chimneys, this right now, because which is a much smaller scale compared to the Fermi bubble, and this structure is very local, actually easily understood by the feedback from stars, current stars in the central region of the galaxy center. And but actually, I think the strongest evidence for the central origin of the Fermi bubble or the Rosita bubble is actually, I think, the absorption line study, which indicates at least a few hundred kilometers per second expansion that automatically requires a huge amount of energy. I think that's at least in my mind, that gives the strongest evidence, which is due to central region kind of explosion, not due to some local kind of stellar event, say a few kiloparsecs away from us, because normally superbubble will not expand as fast.
Excellent point, Daniel.
Yeah.
We'll talk about this more tomorrow. We have 1 minute left. Kirill has one more question or comment, and it'll be brief, and then we'll disperse.
Okay, I'll try to keep it brief, and I guess we can discuss it on the Slack afterwards if people are interested. So this is a very different, right, this is taking things in a different direction. So we talk about sloshing motions of gas in other halos, right? Whether that, as a way to, because it's seen in clusters, because it's hypothesized to maybe explain the structure of kinematics in galaxy-sized halos, etc. So the Milky Way seems to be an example of a system where we've, well, not we, but like, other people who actually work on this have detected sloshing of, let's say, the halo relative to the galaxy itself, or vice versa, right? There's this, at the very least, there's this like Dennis Urkel result from this past year showing the detection of sloshing. Do we think that this is do we think that it might be possible, first of all, to detect this kind of thing? Do we expect the sources of sloshing to be related, between the kind of non-gas and the gas? And yeah, it's sort of more of a discussion question than a specific question.
That's a great segue to having that discussion continue on the Slack. I'm not sure if Tim has his hand up for a second time, but I encourage him to use the Slack as well, which he has. And I think this was a very enlightening conversation. And yes, and we will continue tomorrow. Check the channels, by the way, for after-party discussions, because I think there are a couple that are being planned. And otherwise, if there's no other announcements from any of the other organizers, speak up now if there is. We will see you tomorrow.
I just want to say thank you very much to Edmund, Gurtina, Freeke, Chris, Filippo, and especially Mary for giving such a great talk. So thanks.
This was a very nice session. Thank you all.
Thanks to the organizers. I forgot to thank the organizers. You guys are doing a great job.